Let us now go for a very interesting example, squaric acid. Oh, something went wrong. Okay, now I think it's good. Coming to squaric acid. So this is squaric acid. As such, it is not aromatic because of the presence of these OH groups, which actually leads to different bond lengths. But when these protons are lost, it actually gains aromaticity. Okay. Let me show you that. Now, when this is lost, similarly, when this is lost, okay. See, when these two protons are lost, this is what we get, right? Now, we can call this squarate dianion. Okay. Now, as I said, this is not aromatic due to the presence of OH groups, leading to unequal bond lengths. Okay. So, to gain aromaticity, it loses H plus ion. See, because of deprotonation, it is gaining aromaticity. By the way, it is becoming more and more stable. So, it is in fact most acidic because only after losing protons it is gaining aromaticity. In other terms, in order to gain aromaticity, in order to gain stability, it has to lose protons. So it will, of course, be very much ready to lose the protons, right? Now let us see the resonance structures. Okay, then go for this. Extended conjugation. Now, take this into consideration. Go for extended conjugation in this pattern. Mhm. Yes, it will be this and this. Okay. Now, if suppose I go for this, we'll get the first figure. I mean, this one. Look at this. So, let me just cut it off. So, these are the resonance structures of squaric acid. Greater the conjugation, greater is the stability. Remember, squarate dianion is aromatic, not the squaric acid. Okay. Now I have another example of the same type. It's called proponic acid, a similar one to the squaric acid. Even this also is aromatic, right? Next. Let us see what is homoaromaticity. Look at this. See, homoaromaticity is a phenomenon in which you will have an intervening sp3 carbon. Look at this example, it will be clear. See, this is the sp3 carbon. This sp3 carbon, in fact, interrupts the conjugation. It is said to be aromatic because of some other factors like the thermodynamic stability and some other spectroscopic characteristics, the magnetic behavior, the chemical properties, which are generally associated with the aromatic compound, are also observed with this particular compound. It's actually called homopropylium cation. Okay. Just like the other aromatic compounds exhibit the stability and different properties, even this also exhibits. So this is said to be homoaromatic. I can also give you one more example. So this is cyclooctatetraene. When treated with perchloric acid, the same thing happens. Okay. Now this is the intervening sp3 carbon. Consider the delocalization only till this. Okay. These are the interesting examples for homoaromaticity. Next. Let me write that this is sp3 hybridized carbon atom. Even this, it interrupts conjugation. But these are still aromatic. Okay. See, in case of these compounds, thermodynamic stability, magnetic and chemical properties are the same as observed with the aromatic compound. So this is the reason why even these are treated as aromatic. Okay. Though there is an intervening sp3 hybridized carbon. They are interesting. Okay. The next one. Next. Let us take naphthalene. Some fused bicyclic or fused benzenide compounds. You can also say polynuclear. See, in case of naphthalene, if we see the resonance structures, look at the numbering. This is 9 and this is 10. Interesting. 9 and 10. Now, when we go for the resonance structures of this, let us just change the positions of the pi bonds in the first ring. Keeping this one as it is. Now, further movement of the pi bond. It can be given as now this one goes here. Okay, this one. See, in these three contributing structures, you know, if you consider the C1, C2 positions, and C2, C3 positions. See, in case of C1 and C2, if you observe the number of bonds in these three structures, in the first one and the second one, you got a double bond between the first and second carbon. Whereas in the third one, there is a single bond, right? Now, coming to the bond length, naphthalene C1, C2 bond has more double bond character since it has double bonds in two of the three resonance structures. Consider C2 and C3 also. See, when you go for C2 and C3, in two of the resonance structures, it has a single bond, and in only the third one, it has a double bond. Exactly opposite to this C1 and C2. Okay, of course, because of this double bond character, the more double bond character that it has at C1 and C2, it actually becomes more reactive towards electrophilic addition at C1 and C2 positions. This makes C1, C2 position more reactive towards electrophilic addition. Okay. Now we know that the bond order is inversely proportional to bond length. So if we consider the bond length, C1 to C2, which has got more bond order, is more. Therefore, bond length, of course, is 1.36 angstrom. Okay. And if you observe C2, C3, bond order is less. Let us show that. Two plus 2 plus 1. 5/3. That will give you the bond order. Total number of bonds by the total number of contributing structures. 2 plus 2 plus 1/3 in case of C1, C2. In case of C2, C3, it will be 1 plus 1 plus 2/3. Lesser bond order. Now consider this, this, and this. Okay. Coming to C2, C3 bond length. See, when bond order is less, obviously the bond length will be more. Overall, let us just give because there is some kind of a confusion with the bond length. Bond length in different books they have actually. So bond length, let us say this is less and this is more. Let us simply say that it is because of the thing that bond order and bond length are inversely proportional. Okay. Now let us go for anthracene. 3 fused benzenes. If you observe the numbering, look at this. See, in anthracene, C9 and C10 positions are fixed. We can actually take its 4 resonance structures. In all the resonance structures, remember, the C9 and C10 positions are fixed. Therefore, anthracene preferably reacts across C9 and C10. Okay, that is about anthracene. Now consider phenanthrene. See, in phenanthrene, which is this, now when this is treated with hydrogen, I mean one equivalent of hydrogen, look at how it reacts. Check out the numbering. 1, 2, 3, 4, 5, 6, 7, 8. This is 9 and this is 10. Even this also reacts at 9th and 10th position. This is where you get hydrogen. Okay. Next, let us take one more. It's called triphenylene. A very interesting compound. Now look at these two positions. This is A, this is B. Consider this as X and this as Y. See, because of resonance, of course, X is equal to Y, but A is not equal to B. It has actually got 9 contributing structures. Among those 9 contributing structures in almost all 8 structures, A is a single bond. Out of 9 contributing structures, of triphenylene, 8 structures. In 8 structures, A is a single bond. And see, this particular ring, if you observe, is not aromatic. This phenomenon of some rings giving up their aromaticity to their adjacent rings is known as annihilation. This is very interesting. This particular ring has given aromaticity to the remaining 3, but it has lost its aromatic nature. This kind of phenomenon is called annihilation. Okay. Now check these miscellaneous examples. This one,